Okay, picking up where we left off. I think where we left off was selecting this component, a capacitor. Yep. And this basically to be chosen so that it has the right amount of capacitance to store that energy that the power output needs. Then you could look at this equation right here. Why was it 120 microfarad over 1? Why? Good thing we're following along a design guide, roughly at least. We were basically at this one, the C in, the input capacitor. Selecting electrolytic bus capacitor for universal input. Yeah, the bus capacitor is sometimes referred to as the bulk capacitor, stores and delivers energy to the power system. So it's this one. After the bridge rectifier, we need a capacitor to store the energy at times, so basically when the MOSFET here is open, right? Discharge every half line cycle by low frequency current and discharge continuously by the high frequency current pulses drawn by the converter. So we need a voltage rating first. Wait, now we need a voltage rating, and that's the highest DC voltage that we can expect, which is 375. And the minimum 75. Calculate the average input current of the converters. Select an initial bus capacitor value based on 100. Okay, so we choose this based off of 100. So per 1 amp of input current, the capacitance should be 120 microfarads times the power out divided by the V bus in min, which is the 75, times the efficiency, which gives us approximately 80 microfarad. I did the same thing, so follow the same concept, and I got a value of 47 microfarads. And we selected this component and based off of the C-in voltage rating and the capacitance. Other than that, I don't think it was anything too crazy. 450 VDC, capacitance, ripple current. Yeah. And keep in mind, what we're doing is we're selecting we're making the first prototype. So we will hone in on the values here, every single component we select. But yeah, that's the last thing we did. And according to the next step, that's the snubber circuit or the RCD clamp, which I've written here, RCD clamp circuit, which is the diode, the capacitor, and the resistor. And this part I'm excited for, because I think this is a cool thing where you use the actual characteristics of these passive components in order to make the circuit work and be safe and everything. So maybe we just revise quickly why this circuit is important. I did make a yeah, no, screw it. We'll look at it from this point. So if we have an input signal, it's AC, so it will basically go like this, right? So in the positive half cycle, this part, the current will flow in this direction. Here it will not flow. It will charge up this capacitor. And it will flow through the coil and everything. And assuming this then is on, it will flow through the ground. The magnetic field here will expand or grow, or how to say. Yes. Right, wait. Yeah, and it will go like this then. Back. And then in the negative part, it will go the opposite direction. I still get confused about this part, how to draw it up. So it will go like this, and then in the other direction it will flow this way, yes, through here, and charge up the same way. So here we have a DC current after the rectification. Yeah, and it will go here, and then back again. Right? So, and the changing magnetic field here will induce a voltage on this side, and we'll have current flow through the output diode, charging the output capacitor through the load, and then back, or to ground, I guess. And that's when it's high here. So when this is on, current flows, but the RCD clamp is important in the condition where the MOSFET is on. So in a normal case, we can say like this. We have current flow going through the primary winding of the transformer and then through to ground. I don't know why I'm drawing so much. So going through and then to ground, right? But at the moment where the MOSFET is off, so it's low here. Then the switch is open, right? And the current is no longer flowing down to ground. And because of the leakage inductance that we have here, we get a huge voltage spike. Maybe I can Google what that looks like. Leakage inductance voltage spike transformer. Leakage inductance resonates with drain capacitance. Or here, you can't really see that so good, but so VDS when the MOSFET is on, when it's current flow, it's 0 volt, right? Because it's connected to ground. But then because of the leakage inductance, we'll have a high voltage spike here, which we need to deal with. So the energy from, so when the MOSFET is off, the magnetic field collapses in the primary winding of the transformer. And we have to deal with that somehow. Why we have to deal with that? Good question. I guess it will destroy somehow, or it would stress. I mean, this happened, at some frequency, right? So we can't just leave it there. That's all I'm guessing. We have to deal with that energy somehow. So. And that's basically the equation. E is equal to 1/2. If that's the same. No, it's not entirely the same as a capacitor. We'll get to that, I think. We have to deal with that somehow. So we have a huge voltage spike, and the diode is used in order to direct the current to this part of the circuit. So you can look at it as, here we have a huge amount of energy that we have to deal with for some reason. Let's get back to it later. So the diode is there to direct the current this way. And then we have a capacitor in order to store that energy. Because the capacitor resists sudden changes in voltage, it will absorb the energy from this high voltage spike and charge up this capacitor. The resistor is just there to limit the current, I guess. So it's like you have a big amount of energy here, and when that collapses, it needs to go somewhere. It's like a balloon, right? And the air is coming out and eventually charging up this part and reducing this part. That's how I understand it, at least. And that's what I think is a beautiful piece of circuitry that has a real function, which I still don't 100% understand, but it's still fun to learn. And then this energy is then used again to store, not store, to power circuit. Yes, and what that means is we need a diode that is capable of handling a high amount of voltage. I guess breakdown voltage or avalanche voltage. You'll have a voltage drop, a small voltage drop. Yeah, and you still need a capacitor that handles that voltage rating. Yes, let's look into it. Okay, but that's what we're doing now. RCD clamp circuit. Let's look at the guideline for it. Yes, this energy is then stored in the gap of the transformer core. So that leakage, it's like it doesn't even have to be air or anything there. It's just stored there, I guess. So the leakage magnetic flux is increased and the leakage inductance occurs. Switching current flows in this leakage inductance as well. And the energy is accumulated, but it is not coupled with the other windings. And so power is not transferred, and a surge voltage occurs across the MOSFET drain and source. When the surge voltage that occurs exceeds the MOSFET voltage rating, there is the possibility of MOSFET failure. In order to prevent this, the snubber circuit is inserted to suppress surge voltages. For details, the snubber circuits. The figure below illustrates this operation on the voltage and current waveforms in major nodes. Yeah, so VDS here, you have VDS, it's high. So when the MOSFET is on, right, GS, gate to source. When the MOSFET is on, then when it's turned off, you get this huge spike. And this is what effectively what we have to deal with. Because when the voltage is so high here, it puts stress on the MOSFET. The current flows to the primary winding of the transformer where energy is stored. During this time, the diode remains off. When the MOSFET turns off, the stored energy is output through the diode from the secondary winding of the transformer. Oh, that's basically it. It's not really that complicated, but it makes a lot of sense why you need this type of circuit. So we need to determine a clamping voltage, V clamp and clamp ripple voltage, V ripple. A voltage to clamp any surges that occurs. It is, okay, so we selected a MOSFET with also 800 volts, I think. Can also look into that. And 900. because we had to take into account 875 volts, I think. We just assumed a 400 volt or voltage peak. So we selected 900, but yeah, we can always go down on that later on. The margin is taken to be 20% from an empirical rule. The clamp ripple voltage is anticipated to be approximately 50 volts. I don't always like it when they take shortcuts like this. But okay, for now. Okay. So what we're doing is the RCD clamp circuit. Diode clamp voltage, the clamp. So that's the MOSFET rating then times the 20% margin. Calculator, 900 times 0.5. 900 times 0.8, I mean, which is 720. So we need a clamping voltage on that. So it goes beyond, if the voltage goes higher than that, it clamps to this voltage. And the V ripple was just assumed to be 50 volts. I think that was everything with the diode. But yeah, that's everything it does, right? Because here it's reverse biased. So it's open, effectively. Okay, let's check clamp. ESD protection. TVS diodes. TVS diodes is like clamping diodes, or? Working voltage, clamping voltage. So we need Okay. Can only find one at 648 volts. In the guide, they selected 640. Extremely low clamping. So this is the only one we found. New Mouser. Working voltage 400 volts. Clamping voltage is 648 volts. What else do we need? DC operating voltage 400. Reverse breakdown 470. But for example, this diode right here. Going back to the circuit. Or if I go back to this one. Yeah, okay. So the diode here, it blocks current, right? There's no current flow at all here. So there's no current flow here. When you have VDC max then, which is, let's say 375, that was the max. Yeah, it blocks current, this one. So it effectively works as, or acts like an open circuit here. So does that mean that we don't really have to deal with the reverse breakdown voltage? 470. I mean, we still have good margin. We expect 375 here, right? It might be easy to say that you just say, yeah, it's not drawing any current in that part of the circuit. so we don't have to worry about the reverse breakdown voltage, but I'm not sure if we can just say that so easily. So I have to maybe give it some thoughts. But yeah, so when the MOSFET is off, we have a high spike here, which we assume to be where we determine it based on the margin on the MOSFET then. So the MOSFET can handle 900. We give it some margin that when it reaches 650 or 40 something, it will clamp here. Current will flow in this direction, and we will handle the energy that is collapsed here. Yeah, so that's the clamping voltage, 648. Reverse peak pulse current. Power dissipation, 600 watt. Oh Lord. Wait a minute. Cannot be bidirectional. Let me Google. Yeah, so there is no voltage across. There is no voltage across this diode when the MOSFET is on, right? The current goes in this this way, or this part of the circuit, because it blocks current. So we don't really have to deal with that. That part of the diode is kind of, we don't have to worry about it. Okay, but let's go back. Let's see if I can find a unidirectional one. Oh yeah, we found more. Yes. So what did we say? It had to be 720 clamp let's say at 718 then, or 25? 25. 725, I get 27 diodes. It gives me a lot more to work with. And here still quite high breakdown voltage in case, you have to keep that in mind, but we don't really have to, as far as I understood. Okay, 27, we have a working voltage. Working voltage. Let's just look at the cheapest one. In stock. And also active, ROHS compliant. They're quite cheap at least. We have a through-hole component. Should I stick with surface mount, or I think I have selected some through-hole as well. We will change that out if we have to. Unidirectional, correct. 477. In stock. More expected. So this is from Little Fuse. This is a 600 watt. This is a smaller one. Why is this one cheaper? Yeah, let's just select the cheaper one. So we have a clamping voltage of 725, breakdown voltage, peak pulse current, peak pulse current. Peak pulse current. How to select a surge diode. A lot of good articles. But let's just stick with this for now. It's cheating a little bit, but I would like to make some decisions as well. The V ripple. In the circuit diagram, a diode with a voltage of 800 volts is selected. With this, the resistor. That's really cool, actually. Okay, I skipped a bit ahead and I selected the diode. But it's alright. Okay, so a resistor. R4 is selected based on the following quality. R4. Less than 2 times the clamp voltage times. Okay, here's a little bit better explanation. RCD clamp calculation. I will save that. The RCD clamp circuit is also designed by accounting for leakage inductance that is presented on the connection to the switching node. However, because the leakage inductance is present on the switching node, it also interacts with the drain source capacitance of the switching MOSFET. Together, the leakage inductance and output capacitance create an underdamped oscillation during the falling edge of the switching waveform. So when the switch is off, it creates an underdamped oscillation. This is shown as the V-clamp waveform. So this part. MOSFET is off, we have a high VDS. The role of the RCD clamp is to absorb the energy released by the leakage inductance. Power delivered to this number circuit by the underdamped oscillation is equal to this. This I would like to write down. So power is half L and an I peak squared times the switching frequency. Power to RCD circuit is P RCD is equal to 1/2 times the, I think L leak then times peak squared times the switching frequency. F switching frequency. Here the I peak is the maximum drain current immediately before the MOSFET turns off. Next, we can calculate the clamp resistor value based on the allowed voltage across this number. Note Vs is equal to V clamp and NVO is equal to V fly in the above waveform. Okay. Getting tired. So Vs is the clamp. Yeah. And NVO the above waveform. And this looks a lot like this circuit right here. 2 times V clamp times V clamp minus V or, which is the reflected voltage, divided by the leak inductance times the peak current times the switching frequency. Okay. Okay. Whoops. What happened to... Anyways, this looks a lot like, yes, it's exactly the same, basically, except for this NV out, which is equal to V fly. And I'm not sure exactly what that is. But yeah, the resistor is determined based on this. And we have all this information. In this case, it's using the leak inductance we know, and if the leakage is taken to be 10%, now we already know that we selected a transformer that has specified the leak inductance, so we can use that. We know the switching frequency and the peak current, and we also selected a reflected voltage, VOR or VR. But yeah, I'm glad we started this. So the power that is entering the RCD clamp circuit. So we need to solve it. how to deal with that energy. Okay, but I'm gonna end this video and continue again next time. What is happening with this? Yeah, okay. Thank you for watching.